Well, I'm Brian McDonald. I'm going to be chairing this session, and it's my pleasure to introduce Ron Yurko. So Ron is a PhD student in the Department of Statistics and Data Science at Carnegie Mellon. In addition to the work that he does as far as his statistical methodology research with genetics and genomics, he's a big part of the sports analytics community, is very actively involved in statistics in sports research. He's a co-organizer of the Carnegie Mellon Sports Analytics Conference and Reproducible Research Competition, which is coming up pretty soon, I believe, in a few weeks. And he's developed multiple R packages, including the NFL Scraper package, which has been featured in The Athletic, Wall Street Journal, and 538. And Ron previously worked as a quantitative analyst in finance, and also as an intern for the Pittsburgh Pirates. And he's going to be talking with us today about continuous time assessments of game outcomes in American football.
All right, thanks, Brian. Can you hear me just fine?
Yep.
All right. So let me share my screen. Okay, can you see my screen just fine? Thumbs up.
Yep.
All right. So yeah, I just thank you, Brian, for that introduction. And also I just want to thank the organizers of the conference. I think this really is a testament to the community, to the fact that in the middle of a global pandemic, we are still able to connect in this way, and people from literally all over the world. So I mean, it's a testament to sports analytics, the statistics community. So thank you again for just setting this up and including me in this pretty awesome lineup of speakers. So while the title is this fancy title, I'd say that this is going to be a very broad talk in the sense of thinking about valuing plays in football and how we can ultimately sort of steer towards the direction of better metrics for player evaluation. So to begin, I just want to start with a big mantra of football analytics, and that's the lesson that not all yards are created equal. So everybody knows the case of if it's a third down situation, and let's say on the left-hand side, we're looking at a 3rd and 15, and you've seen the team, they do the typical halfback draw, and that running back will gain, like 10 yards. And that's great from fantasy points and whatnot, but in the end, the team ends up punting afterwards, and those 10 yards were essentially meaningless. Maybe some little gain in field position on the punt. But on the right-hand side, we could have another third down situation where the running back or the quarterback converts, say, 2 or 3 yards to then get the first down. So those 2 or 3 yards are fundamentally a lot more valuable than the 10-yard halfback draw that just concedes for the other team. So this is the whole essence of the fact that in football, context matters. It's not just about the literal event and counting up yardage. It's about taking in consideration what's going on in terms of actually fundamentally moving the ball down the field and maintaining possession. So this has really led to then 2 paradigms that are connected to thinking about how do we actually value plays in football. So that's expected points and win probability. So expected points is just saying, given all the information I have about the team with possession at the current moment, where they're at in the field, the yards to go, down situation, possibly time remaining, how many points is this team expected to score? And then win probability is just thinking of, okay, given all the same information, now accounting for something like score differential, how likely is the team to win the game? And then you can actually value those 10 yards on that 3rd and 15 halfback draw, or those 2 yards on the QB sneak, whatnot, by looking at the change in the start of the play and the end of the play. That leads to these expected points added and win probability added. So we actually do, to arrive at something like expected points and win probability, is we predict different events. So for expected points, the work I've done previously, we focus on predicting the probability of different possible scoring events that could take place for a team. And then we put those together to arrive at expected points. So to sort of visually demonstrate this, the figures on the top show you it's broken up by down, and then you see these lines for each of these possible scoring events with respect to the team with possession. And the color indicates blue being good for the team, and then this darker red indicating bad for the team with the ball. It means that the opposing team is scoring, hence the negative value. So then on the y-axis here are the actual predicted probabilities for each of these events. And then on the x-axis is the yards away from the opponent's end zone. So the closer you are on the left-hand side, the more likely the team is to score a touchdown. The 0 indicates the team is right up on the opponent's goal line and they are about to run it in or throw it in. So what you could see is on a first down, right on your opponent's end zone, the highest probability event is the team with the football scoring a touchdown. And then as you get further away from the target end zone, then the opposing team actually becomes more likely to score. And you see then differences by the down situation as well, where in the fourth down, actually the most likely event is for the team with the football to score a field goal, right? Which makes sense given how teams have played over time. And I'll just add, this is based on our models from 2009, 2017. So this itself could be changing, and especially in recent years. So what we end up doing then is we take all these probabilities for these different events, and then we aggregate them together by just taking the predicted probability, multiplying by its associated point value. So for touchdowns, plug in the 7, a field goal 3, add up those quantities then to arrive at the expected points. It's your expected value of a situation. So the figure on the bottom then just puts these together, again, looking at this x-axis, yards from opponent's end zone. So left-hand side, again, I'm right up on my opponent's goal line. And then the y-axis now are the expected points values. And then each of these lines are for the different down situations, where this bright blue is for first down, and then you keep getting a decrease for second, third, and then finally fourth down. And so just for reference, we actually include here in this figure classical expected points models from Virgil Carter, and then also the Hidden Game of Football, which didn't do any of the fancy modeling that we did, but it's still something that's pretty comparable and close to what we have. Just we get a little bit more variability from accounting for more information. So this is expected points, and then you could literally view as you move between situations, right? From say going on a fourth down on the 35-yard line, and then converting a 1 yard to then get a first down, you could see then a massive bump in expected points value. All right, so that's the purpose then of putting this context, is we can actually give an appropriate value added for players involved, rather than just looking at the yardage that may be really naive. Now, in relation to expected points, something people are probably more familiar with are win probability models. So I'll just use an example of a great Twitter account by Lee Sharp, who he will tweet out these win probability charts. And so this is a summary of a recent meltdown by the Atlanta Falcons a few weeks ago, where they lost to the Chicago Bears. And so you can see the win probability, in a sense, really gives you a story of games over time. All right. And they might themselves may be failing in some ways. And so one of the reasons why I actually chose this example is when we think about win probability and the tail events, the very extreme events, and the high win probability Atlanta had, and yet they still lost. So this is something difficult for people to grasp, but we also don't have that much data on these types of games that take place. So maybe this could itself be fundamentally flawed and doesn't represent any of the uncertainty in these types of games or outcomes. And just for fun, another example I want to show, because I always take joy, the best possible outcome that could happen for a Pittsburgh Steelers fan like myself, for teams like Cincinnati, Cleveland, Philadelphia. I mean, I'm from Pittsburgh, so I naturally do everything Philadelphia does, is when they play each other and neither team wins. And so we could see the mess that took place not that long ago between the Bengals and the Eagles, where once again, once it goes to overtime, win probability models, it's again a very challenging thing. But you could think, though, in this process, right, it's a story of these games. And so Lee has here annotated different events taking place, right? So we could see on this left-hand side, this Zach Ertz catch resulting in a plus 25% win probability, right? We're seeing events that have value. In some cases, then we want to arrive at ways of better quantifying player impact by considering expected points added, by considering win probability added. So what the work I've done previously on these expected points and win probability were ultimately the result of working on this R package called NFL Scraper, which became very popular in the football analytics community, I think. We've had the thing that really jumped out, just to start with, is something like I tweet too much, so I get more credit than I deserve. But it stems from an original project by Max Horowitz. What he started this R package and with the idea of really hopefully leading to the growth of the community for people to access a common data repository and to make it easier for people to get their hands on data. And I really think we've accomplished that, and I'm very proud of that work. And so, but the only reason why it actually grows the way it does is because of the people that use it. So I just want to shout out here in terms of it's really grown people like Ben Baldwin, Josh Hermsmeyer, Kevin Cole, and these specific accounts for different teams. And we've seen people that have used NFL Scraper go on to then work for teams, work for Pro Football Focus, teams in these companies featuring questions about NFL Scraper projects and interviews and whatnot. And that's why the culmination of our work on expected points and win probability was then to include these in these R packages to allow people to then do more advanced football analytics work. Because before, expected points win probability were things that were kind of behind closed doors. So we could provide that out front. And I'm very happy to see that Ben Baldwin and Sebastian Carl have continued this. And because of my short attention span as an academic, I have to move on from NFL Scraper. And they have continued working on and releasing an updated version of the package, essentially, NFL Faster, with their own models that I may disagree with in some ways. But they're providing a great way, a lot of tutorials, a lot of example code for people to then get their hands on data. So if you're interested in getting your hands on NFL play-by-play data and working with it, check out the NFL Faster package. Just Google NFL Faster, and you're going to find a lot of tutorials. It does a great website. So given all of this, given expected points, given win probability, and I keep talking about player evaluation. So how do we actually do this player evaluation steps? How do we go from expected points added and win probability added to really attribute to what a player did on the field? So a fundamental thing about football, right? I talk about context, but also talk about the fact that there are 11 players on both sides during the game, right? So the funny thing was, once we started initially get some popularity in NFL Scraper, the first media hit was Pittsburgh Post-Gazette, where I did this interview and I was talking about it. And naturally, of course, I have to go to the comment section. And as it turns out, my fellow Yinzers provided some great insight in terms of actually how do we evaluate players for football, all right? And they talk about in this comment the fact that, you can't statistically evaluate a running back without evaluating his offensive line. That's correct. Same thing with a QB. You can't evaluate a QB without evaluating his receivers. That's also correct. Stats can only be helpful when an athlete is doing something completely on his own. That's not correct. That is why the NFL doesn't go crazy over stats. It's a team sport on every single play. The only stat that counts is the W. That's a little mixed, but it hits some key points in here, right? Football is a very complex game. It's a lot more complicated than baseball. It's one of the reasons why, maybe it's a little bit more difficult for it to sort of adapt to then embracing data and analytics. So how do we then take some of the concepts in here, and how do we actually evaluate players using things like expected points and win probability? So the challenge of working with the publicly available play-by-play data is you only have information about who is directly involved in a play. So on passing plays, I know who threw the football. I know who's the target receiver. If it's a catch, I know who then made the tackle, who intercepted potentially. And then you have some context, like how far was the pass attempted, just a generic bucket of left, middle, or right. If the QB was hit on the play. We also have information then for running plays. You know who had the football, who was actually doing the run attempt. And then we know to which direction they were trying to run with the football. All right, some information about this run gap between the different linemen. But this is, again, very generic information, and it's manually documented and charted, so it's extremely limited, though, in the sense of we don't have who is on the field for every play at every moment. We don't know what takes place within a play. All we're looking at is the start and the end. We're ignoring all decision making in between. So when I say we, I mean Max Horowitz, Sam Ventura, and myself. We did what we could, we thought, with play-by-play data to try to arrive at a wins above replacement measure by looking at essentially like the average effect that Ben Roethlisberger has on his passing plays. And we came up with a way of arriving at wins above replacement. And this figure on the bottom right here, this shows you the change in WAR over time based on our efforts in this paper that's on the archive. You can check out that. We can see that Big Ben, Antonio Brown, and Le'Veon Bell. One of the key takeaways with and one of another Twitter mantra is the fact that they say running backs don't matter, when it's just the essence of rushing is less efficient than passing. So what we see in terms of our wins above replacement measure, in terms of the value added by these different players, Le'Veon Bell here in the yellow line, he essentially was, over this time period, 2013 to 2017, was like an average wide receiver versus running backs, which were on average lower value, all right, because of his value is really coming from his threat as a receiving running back. But again, this is something that is extremely limited. We don't have any sense of the decision making, for instance, that Le'Veon Bell would make. How much value does he add relative to other running backs when he receives a football on a handoff, given context about where linemen are at, where defenders are at? We don't know how he does in terms of like the cut he makes, the decision he does relative to other running backs, right? This is just the start and end between plays. What we really want to get at is what happens within a play. How can we actually attribute what a player, who gets credit for what within a single play itself? That's how you're actually going to fundamentally arrive at proper measurements of football player evaluation. And you see manual efforts to do this with groups like Pro Football Focus, where they go through and they try to manually grade players on every player, like looking at each individual player, what did they do throughout the play, and they get a grade. Well, how can we actually do that objectively, fully objectively, just based on data? And we can't do that with the play-by-play data. But fortunately, we were able to attempt this once the big data bowl was started, and this is all credit due to Mike Lopez and his efforts. And I just want to say that I think this is the type of example, this competition, that I really hope other leagues will follow, in the sense of, well, I do think hackathons are great. There are a lot of very difficult problems of working with tracking data, that doing a public release that gives people such as myself and others a nice long period of time to really think about these problems and what we could do with the data. Really awesome opportunities then to work on challenging, difficult problems. And so this big data bowl released the first one back in 2018. It released the first 6 weeks of the 2017 season, which in of itself is a lot of data, as I'll show. And NFL tracking data is due from the fact that now all NFL players and the ball have chips, and players have chips in their shoulder pads and the chips in the ball, where now we get the XY position of the players in the football at every 10th of a second. And so there's been awesome work then coming from this just first 6 weeks of the 2017 season of the first big data bowl of Danny Chu and others at Simon Fraser University working on characterizing routes, and work they've continued with the NFL. Samir Deshpande and Catherine Evans on their expected hypothetical completion probability model, and a lot of other great work based on using this sample of data. And so I encourage you to really check out if you haven't. And I think, I don't know if they made the announcement earlier, I can't remember, but the another big data bowl coming as well. It's an awesome opportunity to get your hands on, just try to think about how to work with very complicated data that fundamentally a lot of teams are interested in, see if you can highlight your skills with it. So what does this data though actually look like? And as I said, it's a lot of information here. And so what we have then for literally every player and the ball are the coordinates, these XY locations for them, their speed, and we get a notation of the direction they're facing. And then we get these annotations of different events that are taking place throughout the play, such as when a handoff occurred, when there was first contact, when they reached the end zone, when the ball arrived on a pass, etc. So for the sake of this talk, I'm going to use this example play of a touchdown run. It was a 47-yard jet sweep by wide receiver Cordell Patterson in a game in 2017. I think he was on the Raiders at the time. But so this will be the example play I use throughout. So what we could see is we could take then, there's this giant table basically. Every single row is a player at the 10th of a second. And so we have all of this information for literally every player at every 10th of a second throughout the play and the football. And we could take this table and then we can convert it to actually show us what takes place throughout the play. All right, the tracking data is the embodiment. It's the data representation of the movements throughout a single play. So in this animation, taking that previous table, and the blue dots show the team on offense. I think the Raiders in this case. And then the orange dots are the defense. And Cordell Patterson, he is this black dot once he becomes the ball carrier. So we can see his movements throughout the play as he ultimately ends up reaching this touchdown. So throughout this play, things we might be interested in is thinking about, what is the expectation of the outcome of this play, or how things are going to go at various points. So the second big data bowl focused on this notion of, can you predict where the run is going to end up at given information at handoff? So given this information of where linemen have moved, where defenders are coming from, and how the running back is initially starting, where do we think he's going to reach by the end of the play? And then there could be points of time of, at first contact, given the first contact taking place, where do we think that running back or the person with the ball is going to end up reaching? And then finally, it leads to the touchdown. So is there going to be at some point during this play where we can have a sense of where the person is, going to reach the end zone. So throughout these moments, we really want to get a sense of, what is the expected points at handoff? What's the win probability now at handoff? How it changed from snap to handoff. And then I work on sort of dividing the credit between players, given just a change in a single moment of a play based on the running back or the ball carrier's decision to cut a certain way, or just because of how fast they're moving relative to what the average ball carrier moves at that certain moment, or just due to this lineman successfully blocking this person at this particular spot. So we want to think of then a whole process that goes from snap to then everything in between to the end point of how can then we have like a stock ticker value of expected points or win probability within a single play itself. And so after months of thinking about this, a group of PhD students and myself, along with Sam Ventura and Kostas Pelakrinis, arrived at this whole framework we put together of how we would go about trying to model every basic play in football to arrive at a continuous value, to somehow say we can estimate what is the expected points at a single particular moment within a play, at a single tenth of a second. What is the win probability for a play? And so we could see these decisions that could take place, right? In terms of at the start of a play, a QB could drop back, or there could be a handoff. And then if it's a QB drop back, what's the decision? Is QB throw the ball away? That ends the play, it's incomplete. Do they pass? Who do they then pass to? We have to predict who's the receiving target. And then, do we know when they throw the football if it is caught? If so, if it's caught, we then model okay, who is actually going to catch it? And then once we know who catches it, they have the football and then they run somewhere. If the QB doesn't decide to throw the football, do they scramble or sack? If they do, we again go to the fact of we need to predict where are they going to run to. So everything in the end, what we realize is it all fundamentally comes back to this ball carrier model. So there's going to be all these sort of complicated steps that will each of them themselves take a lot of work and a lot of time. But the final piece will be once a person has the football and their goal, they're not going to attempt to throw or anything. Their goal will be just somehow reach the end zone, or maybe win the game by sliding or whatnot, or stopping the clock. Their goal though is to still move with the football. All right. So what we're going to do is focus then on, once they have the football, predict what is the yard line that they will reach at the end of the play. Because knowing the yard line that they reach at the end of the play, that dictates the context. That decides then what is the update for the expected points or win probability. If I say at handoff, I now expect this running back to somehow get 12 yards and that converts the first down, that means at handoff, I can somehow predict this amazing opportunity, this amazing change in value. All right, so what we want to see is within the play itself, let's try to predict where that ball carrier is going to end up, because that ultimately decides the within play value in terms of expected points and in terms of win probability, where they end up on that field at those charts, those plots at the beginning of the yards from opponent's end zone. This fundamentally decides that. So in terms of then actually doing this, of working with this data and tracking data, tracking data are very difficult to work with, right? It's not just plug and play. You have to somehow take all of these little observations of every tenth of a second and put them together in a clever way of representing useful information about the outcome of interest that you're trying to model. So in the case of thinking about modeling where the ball carrier is going to go, we want to look at the ball carrier here in black and think of, how far away are they from the nearest defender and other defenders? What is the angle between these players? Is this defender even running in the correct direction, or are they being blocked by somebody? Or how far away are they actually from the target end zone of interest? What direction is the ball carrier facing themselves? You have to take that XY data and you have to work on actually constructing it and doing proper engineering to then have something useful. All right, so this is the most important step, arguably, of any work with things like tracking data, is how do you actually make use of it in an efficient way as well, and things that are related to what you're interested in. Something that is very popular approach for working with tracking data, or known as Voronoi tessellations. And so there's been a lot of work by the group of the Luke Bourne lab of taking where you have positions of where players are at on the field and using things like what direction they're facing, the speed, etc., and breaking up the field into these partitions, these tiles, to give you a sense of ownership. And so what we do is we take information like on the previous slide of like the direction and distance between defenders, and then we also summarize, for instance here, like the size of the area that the ball carrier owns in terms of this tessellation, and things like does it contain the end zone? How much does their team own? Is it connected to what they own? We try to summarize variables that have all of that information as well. So most of the work of working with tracking data is a lot of engineering and data wrangling and mungling to just understand and try to extract something useful out of it, to then arrive at the process that you're going to use it for your model of interest. So all of this information then, it leads to a very complex situation. You fundamentally have a lot of variables, so a high dimensional problem. We're going to have things that we don't think are just a simple linear model. All right, so what I mean here is I'm dealing with something very complex. It has a lot of these interactions between variables. Potentially the distance between this defender and the angle they're facing could have some interaction. The speed they're running at with the defenders. And also, in this context, there can be a time component of maybe knowing information about previous parts of the play can provide some predictive power at knowing what the outcome could be, not even just at the current moment. So how can we use that structure as well in terms of modeling? And what we end up doing is we view some very complex models. And the one thing I want to, because this is a thing also for undergrads, high school students, is anytime you're trying to think of building a model or trying to evaluate something you're creating, you need a baseline. I can't just say, I'm going to take all of these things I summarize, I'm going to throw it into a fancy deep learning model, and wow, look at that, it's amazing. No, I need to evaluate it against something. So what we do is we take different steps, different sorts of models at different levels of complexity. And this intercept only, this is a model that it ignores all variables. It's looking at the variance in the data. It's just saying, if I just use the average, if I just use the average yards gained, and as I predict that for every single moment, what will be my, I use no information at all. So if I just use the average without any information about how I summarize the player tracking data, how well do I do? And then these different models vary in terms of their complexity. I'm not going to go into the details of this, but the last two here on the right, these are these deep learning models, where the one on the right-hand side, this LSTM model, long short-term memory, this is the only one of the ones we considered that accounts for this time component as well, to include previous steps of information within the play itself. So in terms of then doing these different considerations of models, what you want to actually do then is have some way of validating and comparing these approaches, that with the emphasis of how well does a model I build generalize out of sample. So if you're thinking of what a football team would want in this case, they're going to have a model that then they're going to want to apply to new football games. All right, so if I have a model that cannot generalize to data it has not seen before, then it's not useful. So what we do is we evaluate our models based on a leave 1 week out cross-validation approach. So all this means is I'm going to build a model, for instance, on the first 5 weeks of the season, and then test how it does on the holdout 6th week. And then I just rotate between the weeks, hold out the first, test on 2 through 6, hold out the second, test on 1, then 3 through 6, so on. And what we then measure is like this overall error rate, and then we also look at to see how do these models compare over the course of these ball carrier sequences as well. And so what we could see, what we end up arriving at was the model, this LSTM model, this model that has all of these sort of levels of complexity of dealing with high dimensional interactions. We're looking at then in this time component as well, it has the best overall performance compared to the other models. And so the way they interpret these plots, the y-axis is this error, this RMSE value, right? How we're measuring the error between the different models, and the x-axis is the frames, so the 10th of a second from the start of a run, essentially. So what shouldn't be surprising is at the very beginning of a run on the far left-hand side, you're going to see a lot of error. All right, the error is going to be higher for all of these models, right? That's in a way that's where you viewed the least amount of information at the moment of at the moment of handoff. And then once we just get 10, 20 frames in, that's where then the model starts to learn, and that's where it starts to really improve relative to, say, in the top left here, this intercept-only approach. And so you can see the intercept-only approach really does bad throughout time, all right? But the thing that's interesting is while these different other models, Lasso, XGBoost, other feed-forward neural network, start to do better than the intercept-only approach, later on, they actually do worse than it, all right? The LSTM model, by having this time component, was the only one we saw that then actually achieved a lower error than this intercept only and did it throughout the course of the run. Just to make this clear, the how dark these bars are throughout the course of the run just indicate how many of the observations you have. So every single ball carrier sequence, these are very dark on the left-hand side because they have all of them have a start of a run, but there's fewer runs that have over 10 seconds in length or whatnot. So this is another justification then. This is a justification that we see as a usefulness of using this LSTM model. And as another way of looking at it, instead of just this RMSE error rate, we also evaluate based on if we just look at the actual value of the error to see if there's any sort of bias in under or over predicting over the course of a run. So what shouldn't be surprising is the intercept only approach, this baseline approach, is a biased approach for then predicting over the course of the run at various points along time. It's biased because we can see it's systematically different from zero. What we want is a model that's essentially hovering the zero line the whole way through. And what we can see is this LSTM model does the best at that versus these others we considered. So in this case, this most complex model that we use was actually the better approach. And this was the reason why we wrote this paper called Going Deep, because we use a deep learning model, because that is a fad. All right, so once we have this, now using the same animation from before, but now I'm plugging in this red line to give you a prediction. This is this LSTM's model predicting, once Cordell Patterson has the ball, where are they expected to land, or where are they expected to reach at the end of the play? So we can see how it changes over time for these different moments to then see where they're expected to reach a touchdown, and expected at different points. And so one of the things is we can have a clear sense of like the impact different variables have on these models. And so for instance, on this left-hand side here, this time into play along the x-axis, the y-axis is this distance to the closest defender. And what shouldn't be surprising to you is the first contact, the distance is greater than 0. Tracking data, none of this is perfect, right? So don't expect, if you ever get your hands on to work on this, a big data bowl that is going to be very clean. But it still is something that gets close to 0. So you can see how that changes over time with respect to this red line kind of going back and forth. But one thing that's interesting here in this example run is the fact that he maintains a high level of speed throughout the course of the entire run itself. As I said, though, what we want to do is take the expected yard line, and we're not just interested in that. We want to get value added. So we want to convert that to expected points of win probability. And as I said before, this is actually simple. We already have these expected points of win probability models, and we could just take this prediction and update, if I expect them to reach this yard line, what's my new predicted expected points of win probability? And so what we can do then is plug in those estimates to then view the stock ticker value to see what is the expected points, how does it change over time over the course of this run? And also as well, the win probability. Once he starts moving further and further down the field and he's expected to reach something like the end zone, right? He reaches these points where we think he's going to get a touchdown. So then his expected points is 7 points. However, note of caution on doing this. This is not the expectation of expected points or win probability. All right, all I've done here is I've taken a single predicted value, my expected end of yard line, and then I was plugging that into predicting the expected points and win probability. So I'm using the word expected a lot. I know this is going to cause confusion and give you a headache, but this is a single point estimate value. What I really actually want to arrive at to compute the true expectation of expected points or win probability that you learn about in your intro to statistics probability class when you're learning about continuous distributions is I actually need a full distribution for the end of yard line. All right, I need to actually get a sense of what are all of the possible outcomes that could take place over the course of the run that I think have some likelihood of happening. And then I'll actually be able to arrive at what should be a much smoother representation of this expected points or win probability. These are very jagged, all right? I don't actually even think this is proper in some cases. This avoids any uncertainty I have about where the ball carrier could end up on a play. So what we then do is we don't just use a single point estimate value. We then actually model the full distribution of potential outcomes, essentially, that the ball carrier will arrive at on the field in terms of their end of yard line. So once the ball carrier gets the ball, now I have all of these red lines indicating various points of likelihood that they will arrive at. And we do this with a technique known as conditional density estimation, where this was essentially building off a thesis work by Taylor plus Fissel of using random forests, so another high dimensional complex model, to then model in a non-parametric way the full distribution of the end of yard line. So what you see is some like bimodal structure where the darker the red is, the more likely we think, the higher the density that the player will have of going at that location. So what we could see over the course of this run, for instance, is once they get the ball, we start to have some more likelihood here, and then it really darkens at that one particular point. But then the target end zone, as you can see, gets this thicker red line over the time, because this ends up becoming the more likely destination of the run. There's still some non-zero chance that he gets tackled to close to where he's at. But we start to see this opportunity over time. And so this is just a still shot then of showing this bimodal structure of once they have the ball, how likely do we think just where they're at the particular moment versus there's some non-zero chance that we think that the ball carrier could arrive actually at the end zone. So once we actually use then this full distribution, now on the right-hand side, now we actually have the proper expected points, expected win probability. And you can see this is something that's much smoother. It doesn't have the jagged spikes as before. So how do we then actually use this whole process I just went through? I talked about the beginning of, I want to arrive at better player evaluation. And this is actually fundamentally how we're going to do that. The first step was to how do we properly value within a play? And there's still a lot of work to be done in this. Didn't fill out all these rest of these steps. I will say though that Matthew Ryers, Simon Fraser, he's done recent work, and you can check out his Twitter account of basically implementing the quarterback decision models that we described. And he goes into a full better quarterback decision rating. That's fantastic work. And one of the things I hope for undergrads and high school students watching this is I'm only here because I tweet a lot and share my work online, and we try to promote this NFL scraper. And it's successfully worked, I think. So I want you to be aware of, do not be afraid to share what you're working on, get feedback, and don't be afraid to promote it. It can feel awkward at times, but people aren't going to see what you're doing unless you get it out there. And once you get it out there, then they'll reach out to you, be interested, you'll get feedback, good criticism, and improve. And so examples of this on the left here, this was a project by Sarah Malapalli where she scraped NFL next-gen stat images for pass dot locations. She converted images to data sets. And she is the quickest way of ever getting hired by an NFL team. She now works for the Baltimore Ravens. And then on the right, Rishav Duda, former undergrad at CMU, software engineer, he's recently done some awesome work of imputing the third dimension to the tracking data using simple physics that I don't understand, but he figured it out. So, given that, I want you to know that this next, that working with tracking data is very complicated. It's a lot of hard work, but these are going to be the steps. And this is where people are interested in if you're thinking about careers in sports as well, to ultimately better arrive at, especially within football, better true estimates of player value added. So just want to conclude by thanking the others that worked on this and our team for going deep. And then make sure, as Brian mentioned at the beginning, you check out, we have our own conference coming up in a couple of weeks, the Carnegie Mellon Sports Analytics Conference. So that is completely open for registration now. And with that, thank you. And any questions?
All right. Thank you, Ron. Please join me in thanking the speaker. You can probably only hear one clap right now, but I think probably there's several dozen people clapping by themselves at home. So let's start off with the questions here. So this question is from Will Riley. How is expected points adjusted depending on what the player is being asked to do? So if a player is put in a position where he's set up for failure, for example, a yards after completion reliant receiver asked to get open on his own, does the data still suggest it was his fault? How can teams take into, hold on, this is a couple part question here, into account the reason for changes of EPA in a play?
Yeah, so that's a great question. And that gets at the point of why you want to do this continuous time value, right? In terms of, if we consistently hear the statement of, running backs don't matter, all right, because it's just not as, rushing plays are not as efficient as passing plays. So given that we can know that, and given that a running back gets the football on a handoff, and the expected points at the moment of handoff may not be that great because we know it's a running play. But in the end, that running back themselves still ends up adding more over the course of the run relative to what others do. And by using the information, the tracking data, assessing, the lineman locations and whatnot to get a better sense of the expected points at those particular moments, then we're actually able to say, yes, okay, the running play itself wasn't that valuable, but maybe Christian McCaffrey is better still at those situations than other particular running backs, right? So it's still a way of trying to figure out how better players are relative to others in the same scenarios, right? So, it's absolutely a thing where if you just look at this raw expected points added, win probability added, you're not going to get a sense of, if you're just gonna look at it and see, well, they're still net negative. Well, okay, the expectation is net negative. Now, with respect to that, do they improve versus how others do as well?
All right. Question from Marcos. Hi, Ron. Do you think hybrid models, machine learning plus stochastic, are competitive to deep learning approaches? For example, XBoost, he might mean XGBoost, plus temporal random effects.
Yeah, no, that's a great question. If honestly, it's something we didn't look into as enough. And I'll say, I mean, I wouldn't be surprised if with a lot more clever engineering of variables, if the lasso could have been almost just as good as the deep learning model. I mean, it's complicated in the sense of tracking data. There's a lot of information, and maybe we ended up while we did a lot of hard work on constructing variables, it was still in a way a little lazy versus what we've seen, I'll say in the big data bowl entries. I know the winner of the second big data bowl, I'm pretty sure they used a convolutional neural net, which is just thinking of, let's view the tracking data as like an image, and trying to like break up locations that way. So, I mean, potentially, thinking of XGBoost or random forest would, maybe with a little bit more engineering could probably do just as well, if not better. It wouldn't be surprising to me. I personally, I'll say this about something like deep learning is when you work on it, when you view the results of it, it's like, wow, this is amazing. It's a lot of hard work and construction to get it to be something that is working in tune properly. Something like XGBoost and random forests are very easy off the shelf. Deep learning is not, neural nets are not easy off the shelf. So that's just something else to keep in mind.
All right, question from Devin. Hey, Ron, do you think there's value in predicting not just expected tackle position in the X dimension, but also in the Y dimension?
Yeah, that's a great question. So in our case, because we were using our expected points of win probability models that ignore the Y dimension, we just focus on the X dimension. But there could be something to be said. I mean, I don't know if there is any fundamental difference in an expected points or win probability model, even just between play, given X, Y, right? Given side information on the field. Maybe there could be something there. And in that case, then it would be more valuable to do the XY prediction. But for our case, just because all we needed was the single dimension to update expected points of win probability, we viewed it as something that makes the problem simpler, right? Because if you just try to predict the joint distribution, the joint outcome of the XY, that's going to just add more complexity to which it's already a really complicated problem. And you'll just deal with more struggling models in some case. But it is a good question. There could be some differences, useful information there. I don't know.
Okay, we've got about 4 minutes left, so we'll go with a few more questions here. So this is from John. If we had consistent data for who is on the field for each play, could that lead to optimal line formation? And when I replace a player, does it make a cohort better or bring a cohort down? So For example, when X and Y are playing and Y gets hurt, does Z make X better or not? Are we able to get this player time on field data from the NGS data?
So working with the next gen stats tracking data, right? The player tracking data, you absolutely know every player that was on the field at every particular moment. So, I mean, the logical next steps in some way is trying to break up the stock ticker value in like a plus minus approach of you see with like hockey work Brian has done, and NBA regression plus minus approaches where you're trying to like credit players at these particular frames, maybe based on even like the direction they take or whatnot. Because like the play-by-play data that's publicly available, we don't have who's on the field at every particular moment. So like the goal would be to try to answer your questions, right? Of like if we plugged in Juju Smith-Schuster on this passing play, does he do better than someone else? Like, I mean, fundamentally, we're all interested in like that causal question. I don't think we're quite there yet, but it's still like that's the goal of what we're hoping to do by doing these better valuations. So I don't know if I answered that question at all. I feel like I kind of rambled, but that's like the goal of what we're hoping to do.
Okay, the question from Steven, how can expected points and win probability models be used in real time during the course of the game?
Yeah, that's an interesting question. I remember I was actually asked this question by the crew of Wharton Moneyball, and I think I botched the answer then. I'll say now, I don't think the goal is to really think of like during the game, can it lead to a better decision? Like, I don't think that's a practical thing. I think this is really about we can now try to objectively measure the contributions of everybody throughout the play and do it after the game. All right. Of actually looking back and what were the values added within these plays by these players. Because right now we don't have all of these metrics about linemen, about cornerbacks, about all these things that we can't measure. There's no counting stats for these different players that then the tracking data can lead to. I don't know about within the game itself. I would have to think about it more like what's practical. I view this as how we actually can now go back and properly create new statistics to summarize player performance.
Great, thanks. And with that, it is 10:50, so we're going to have to move on to the next part of the conference. And thanks again to Ron for presenting his work on this continuous time evaluation of game outcomes. And if you had a question, there's a bunch of questions here that we didn't get to. If you had a question, please feel free to reach out to Ron after the conference or during a break or something like that. And I'm sure he'll be happy to answer your questions. If you ask on Twitter also, he'll respond to you on Twitter. So with that, I think we'll turn it over to June now.